Good. Okay. Welcome to section 10 or something. Today, we're primarily going to go over the answer key for problem 4. And then we'll also talk about how to use JAGs and write a JAGs model. So this problem set was challenging to people. I think a lot of the difficulty that we seem to have on courseworks was, well, the two kinds of difficulties. One, difficulty just getting the data into the right condition to estimate a model, dealing with the fact that you had NAs everywhere, and then you could make interactions that didn't have any observed people for that category, and then the number of columns in X might not line up with the number of coefficients that you were trying to estimate, and all kinds of difficulties like that. And that is sort of inherent to the research process. Not that we were really doing any actual research on the problem set, but we were doing something that was, an imitation thereof. And in a manner of speaking, the missing data stuff will be simpler when you don't have to worry about lining up X's and, all kinds of stuff like that, because you're just going to, deal with the data with the NAs. But it's much harder to come up with a reasonable model for also drawing from the posterior distribution of the missing values. And then to just, do something like complete cases like we did on this problem set. So there's, a trade-off there, definitely, and we'll start talking about missing data stuff next week. Then, the other part of the difficulty with this problem is that, I probably should have only given you like 10% of the data set or something like that, so that you could go through the cycle of debugging and looking at the output and stuff a little bit better. I didn't want to make it too small, because then I would have exacerbated the problem of not having some observations for some of the interactions that anyway. So I just gave like 25% of the data set, and then because different people were choosing different models, got into situations where some people use questions that were asked in a lot of years, and some people use questions that were only asked in a few years, and that led to some different issues, which we'll get into. And then, even if you got it running with that sort of data set, estimating a lot of parameters, and it didn't necessarily run very quickly. Again, that would probably depend on the computer that you were using, whether that turned out to be like a reasonable but long amount of time or an unreasonably long amount of time. But the reason why we do non-trivial computing problems is, and this is what I mentioned I wanted to say before, is that I think a lot of the stuff out there that you might read understates the problem that you never exactly know whether things are working well. And if the only problems that you practice on are the problems that are like generated data or you constructed to go really quickly and always converge, and then you can look at plots of the outcome and just analyze it, I think misses the 90% of what it means to be a Bayesian, quantitative researcher. And that's, to think about writing the code as efficiently as possible, to run into all the problems that, you run into when you're actually trying to apply this in research, and to figure out a way around them. And I think it didn't go so great this week, because I didn't recognize the problem that a lot of people were having with it being unable to initialize until like last night. So we didn't have a chance to go through that, but we will go through it now, and I'll tell you what I think was happening. But again, because different people were doing different models, it might be that there's something about the model that you were doing that was a little bit different. So we just start going through this. First step, loading everything that you need into R, and different people could choose different models. I chose one for support for gay marriage. And so there's 5 ordinal answers: strongly agree, agree, neither agree nor disagree, disagree, strongly disagree. And one thing about it, just to sort of preview some of the missing data stuff that we'll talk about next week, questions like these are going to have a lot of people who don't answer in those 5 categories. Any politically sensitive topic does, but there was like affirmative answer choice of can't choose. And that's one that you need to sort of think about is, can't choose equivalent to neither agree or disagree. Usually if somebody like strongly agrees or strongly disagrees with the idea of gay marriage, they know that. So I don't, my sort of sense of questions like this is you don't get people who are sitting there thinking, well, do I strongly agree or do I just agree? I can't choose between strongly agree and agree, so I'll put can't choose. I think, most of those are probably people who are genuinely conflicted, or they don't want to say, or they probably a lot of them do strongly disagree, but they don't want to say that on the survey, or something like that. So you need to think about what sort of answers really constitute missingness and what don't. Now, so the sort of obvious missingness is this question was asked like once in 1990, and then it got started asking regularly in 2004 through 2014. So the many years that the general social survey was administered, but that question wasn't part of the survey, those are, in a manner of speaking, missing, although it's not missing due to any characteristic of the individual. So we tend to not worry about those as much unless we're Don Rubin, which we thankfully are not. If you're listening, Don, I love you. I don't think Don does YouTube. Anyway. Yes. Drinking whiskey and listening to YouTube. Yes. Anyway. The model for an individual year can be expressed as the difference of 2 CDFs, the cut point relative to the linear predictor, and it's easier to just imagine having cut points at the end of negative infinity and infinity to not have to explicitly write down the 2 cases. But when you do it in the code, one of them is just going to be 1 minus a CDF, and the other one is just a CDF. So you could choose a variety of predictors for a model like this in an attempt to be somewhat exogenous. I chose age and sex and religion, but not the person's like current religion, but what religion they were, their family was, I think, when the person was 16. Some people think that beliefs about social issues are more formed in adolescence and stuff like that. So in any event, that's a model. There's a bunch of religion categories, and those get made into dummy variables. So if we try this in ordered MCMC oprobit, the first thing to do is to create a data frame that only has the complete cases. And there's a variety of ways that you can do this. Maybe the most elegant way that I know of is to use the model frame. That takes in a formula and a data set, and it returns a data frame that just has the complete case of Jasper.
You know, a good way so let's say you want to get a model frame style object for like a model that doesn't have an intercept, right? I know you can put -1, but it actually only like removes the intercept for the first variable. Do you know of a way to get like easily get matrices that doesn't require doing all that stuff with contrasts, where it just dummies out?
No, but at that point, you're sort of already at the thing where the way of ours doing interactions is kind of inconvenient anyway. But no, I don't know an easy way to do that off the top of my head.
I mean, because Stata can do it.
Yes.
I feel like if Stata can do it, damn it, ours should be able to do it.
Ours should be able to do it, but I don't know of anyone who's written such a function to easily do it. The next line, so in model frame, it's only going to keep the observations that are complete, but the year variable is still going to have categories that are empty for all the years in which this question wasn't asked. And so if you just pass that thing to the factor function, by default, the factor function drops unused levels. And so the year in the MF data frame only has like 1990, 2004, 2005, up to 2014. And so then you can do this in ordered probit. If you do it in parallel, remember to, or even if you don't do it in parallel, if you just do multiple chains, remember to pass different seeds so that you get different answers. And to circumvent some of the problems with, I don't think we had any, well, we would have had some religion categories were not observed in some years. It's good to pass a starting value for the betas, and it's good to put a proper prior on the betas. So this is identity precision matrix. And so if you give it beta start, it doesn't have to do maximum likelihood to find the starting values. And some of the errors that people were putting on Piazza were attributable to the way in which it's trying to find starting values for beta by calling the maximum likelihood thing. And if you have, you know, hundreds of interaction terms, the maximum likelihood estimator might return an error, and it might be the case that some of those columns are all zeros for the interactions with categorical variables. And so can get around the problem that way. The tune thing is kind of important, but you need to play around with it a little bit. So the MCMC ordered probit is mostly a Gibbs sampler. So it draws from the full conditional distribution of beta. It draws from the full conditional distribution of Y star, but there isn't a full conditional distribution for the cut points. So one of the intermediate steps in each iteration is a Metropolis Hastings step within a Gibbs sampler. And it does Metropolis Hastings to update its cut points. And sort of counterintuitively, the most efficient way to do Metropolis Hastings for models that are kind of sufficiently normal is to drive the acceptance rate down to 0.234-ish. And so that basically means that 3 out of 4 iterations, the cut points are not being, the proposal for the cut points is not being accepted. So it stays the same. But the 1, you know, out of 4 times that it actually accepts the proposal for the cut points, they're relatively far from where the cut points are now. And the fact that it can make one big jump turns out to, you know, be kind of optimal for getting a good effective sample size. I don't think it would make a whole lot of difference in this case, but you can play around with different values of tune in order and look at the output of it to see what looks like it's achieving a acceptance rate that's close to 0.25. And then, you know, you could run a thing with more iterations or something like that. By default, if you look in the documentation of MCMC Oprobit, tune is set to 0.05 divided by the number of answer categories in the outcome variable. And that's usually in the right ballpark, but you could change it. So there's 5 answer categories here. So I made tune a little bit bigger than the default in order to get a good acceptance rate. And then, so you can run that. And then these gray lines are not too easy to see. I also didn't realize that there was no obvious way of only looking at autocorrelation of some parameters in CODA. I don't know why they haven't implemented that. I assumed that they had implemented that when I wrote the question. So really, I guess you have to get the autocorrelation for all of these, but you can use a knitter trick to only keep the last plot in a chunk, and gammas come out last in the posterior distribution. So that's how I got just these 3. But if you put all like 200 or 200 times 8 autocorrelation plots into your PDF, that's fine. Alvin can scroll through them. But anyway, the point that I was trying to make with this autocorrelation plot is that the autocorrelation dies out pretty slowly. I only put 8 or so lags out, but it doesn't seem to be getting a whole lot smaller from step to step. And that has a lot to do with the fact that, out of 8 lags, it probably only updated, twice. So by construction, there's going to be a fair amount of autocorrelation. But if the gammas are not mixing well, then the Y stars are not going to be mixing very well. If the Y stars are not mixing very well, the betas are not going to be mixing very well. And so this is an example of, although there is a Gibbs sampler, and most people would find the interface to MCMC Oprobit easier to use than doing something in Stan, you can get a lot better performance from Stan in terms of the efficiency and in terms of the flexibility to be able to do different models and whatnot. That it's good that that is available. And in a problem like this, I think it handles the time varying covariates in a easier way to manage than what MCMC Oprobit has to do with all these interaction terms and stuff. So did everybody at least manage to get through the MCMC Oprobit one? Yeah.
I just want to say, if you want to grab just one parameter and do an autocorrelation plot for that with the MCMC with CODA, it's not that tough. Like, there is a way of doing it to just grab one parameter.
Okay, well, I don't know what that way of doing it is. I assumed it existed, but then.
I'll send the,
oh, okay. Or I'll see it in your answer key, I guess.
Took me a long time to figure it out, but it's possible.
Yeah, I mean, I guess you could convert it to a matrix and just use the regular autocorrelation function.
You don't even have to.
Anyway,
I'll send it to you.
It wasn't a huge aspect of the problem that you should have been able to anticipate in advance that the autocorrelation would be very high out to a large number of lags. And so if you managed to see that, then that was the essence of the question. So any more questions about that one? No? Okay, posterior predictive distribution might have been easier than people made it out to be, because to draw from the posterior predictive distribution in 2014 or whatever is the most recent year that the question was asked, you don't need all the interaction terms. The only pieces of information you need are the cut points, which are common, and then the coefficients on the predictors in the baseline year, and the interaction term, which is to say how much those coefficients change relative to the baseline in 2014. And then, Anna?
I have a question on that, because isn't it easier to just get a model matrix with all the everything, like all the dummies, all the interactions, everything, and just multiply it together?
Uh,
To take care of it.
If you were in a situation where all your X's, none of them got dropped
Right.
along the way, then perhaps that is easier. It's a bit wasteful because you're multiplying a lot of zeros by stuff,
Right.
but it could have been faster.
Yeah, it's one line of code instead of.
Yeah. A lot of people, their designs had X columns being dropped and stuff. So then getting it all to line up was challenging for them. So, what I did here was I created a model frame for 2014, subsetting on year is 2014, made the X matrix that corresponded to that, which I guess had like 600 or something observations. And then what I needed to do was go through and add the interaction term for 2014 to the baseline parameters. And that gives me the combined coefficients on these X variables for 2014. So this X 2014 only had 15 columns or so, one for the intercept, one for age, one for sex, and then a bunch for the religions, but not like hundreds, due to all the interaction terms. And so then you just need to select the relevant columns. So for me, those were the intercept, age, sex, female, and any variable that started with religion 16. So it was like religion 16 Christian, religion 16 Jewish, and stuff for the different religion category dummy variables. And so, you could have done this just by looking at what the names of the posterior matrix are and just indicating them by number or something like that. You can do it a little bit cleverly with a regular expression to pick out the ones that start with religion 16 in my case, but you didn't have to do anything that clever. And then add it to the corresponding things for 2014, all of which start with the prefix year 2014 for the interactions involving 2014. So if we just add...
Marcus, what about the constituent term for 2014?
Yes. So that it got wrapped up in the year 2014 on the intercept. And I probably should have printed out the names of the posterior matrix so you could see them. In any event, that beta 2014 has the same number of columns as the X 2014. And so then we can do the thing that we've done before, drawing from the posterior predictive distribution. In this case, it's a bit artificial because I wanted to make the histograms on the next page. Usually you would not just draw from the posterior predictive distribution of the latent thing and then stop. The great thing about posterior predictive distributions is that you can put your conclusions and stuff like that in terms of observables. Although, as pointed out in Rubin et al. Article, there's no causal effect that can be written on the observables involving just the difference of means that's not model dependent. So in any event, in this case, we're just drawing from the posterior predictive distribution of Y star. For each row of that X 2014, we take out one row of that, call that the vector X, multiply that vector by the posterior distribution of the betas for 2014, and then draw that number of times from a normal distribution with a standard deviation of 1. And we get out all these draws of the latent variable for people who were surveyed in 2014. And then, so this histogram didn't come out exactly what I had in my mind when I wrote the question, but it should have looked something like this. You need to get the posterior means of the gammas to use as cut points, remembering that MCMC oprobit estimates the intercept but doesn't estimate the first cut point. It fixes it to 0. So you need an additional cut point at 0 in order to create a histogram that looks like this, which is really not what I intended. I mean, if that's what you did, then that will be full credit, but that's not really the histogram I intended to make. The histogram I intended to make look like this, where we made a sequence of breakpoints, etc., and then I was going to color them in based on where the average of the posterior cut points are. So the first cut point is fixed to be 0. Everybody who's latent utility is to the left of that. Under the model is going to be answering the first answer category, which is strongly agree. So I guess that it had the same amount of area under strongly agree as in this one, but it looks messed up there. Any event, so by 2014, a lot of people predicted to strongly agree with gay marriage. Then narrower sets of people in agree, neither agree nor disagree, or disagree. So the cut points for those categories pretty close together. And then, still, pretty substantial proportion of the people strongly disagree. So that's the histogram I had in my head, which, except for the fact that this is a latent variable, would be like a pretty reasonable way to convey the conclusion of your model, and to also convey what's going on with one of these ordered models where the cut points are chopping up a distribution and using that to give you a conditional probability of being in each answer category. So even, if you're answering strongly agree, you have a probability of only agreeing, or, all the other answer choices. So there is randomness to it, but that is sort of the distribution of opinion implied by the model and how the model would chunk it up. So it looks like that.
Is there something just like mechanical in these models that makes the extreme categories the most likely ones? Because there's sort of like the residual categories that get everything from like negative or positive infinity to...
Yeah, so they have a lot of, they go out to infinity and negative infinity on the horizontal axis, but the amount of area, on the side of the cut point can differ. For this issue and a lot of, political, social issues, we tend to see people, either strongly agreeing or strongly disagreeing about, basically everything. So, we see that here. If I did maybe a less political question, then we might see more area in the histogram in the intermediate categories. But I think it has more to do with the data that you're analyzing than any characteristic of the model. Yeah. Questions? Okay. So turning out to do the same model in Stan, or at least the same likelihood in Stan. In a manner of speaking, it can be done easier by indexing the coefficients by time rather than multiplying to create a whole bunch of interaction terms and just multiplying that sparse design matrix by a big vector of coefficients. Of course, you could generate a X matrix with a whole bunch of interaction terms in R and pass that to Stan and estimate the model with a giant vector of betas. In addition to, I find that less intuitive, but there's a reason to not do so in Stan. And the reason comes back to it has to keep track of the derivatives of everything. And I'm not entirely sure to what extent it has this now, but if it multiplies, it doesn't skip multiplying by 0. So if it takes some unknown beta and multiplies it by 0, it's still having to put a term in its tree to keep track of the chain rule that's just going to be 0. So obviously that is going to not contribute to the chain rule, but it is something it has to allocate memory for and keep track of and sum over. So that is to say, Stan in general does not currently have any sort of a sophisticated way of doing sparse matrix algebra. Sparse matrix algebra being matrices and vectors that have a lot of zeros in them by construction. And even if some number is like very close to 0, to the point where it makes absolutely no difference at all to the conclusions, it still is multiplying that. It's still keeping track of a derivative that's like 1 times 10 to the negative 20th or something like that. And so that it takes up the same amount of resources, whether that's a relevant number or a not relevant number. So if possible, for the time being, you want to avoid doing unnecessary math operations. And one way to do that in this case, and what I also think is a clearer way to understand these models, is to just have an X matrix with a handful of variables, not interacting everything with year, and then doing what we've done here, make a array of vectors of length. Each of the vectors is of length k. K in my case is about 15. And we have a collection of vectors of length 15, that collection being equal to the number of years that the question was asked in your data set. And then you can just refer to the index of beta in order to extract the relevant coefficients for that particular group. We also need to estimate the cut points. In Stan, unlike MCMC Oprobit, it's easiest to estimate to fix the intercept to 0 and estimate all but one, or n categories minus 1 cut points. Again, the way MCMC Oprobit does it, that has to do with the fact that it's doing Gibbs sampling for the most part, full conditional distribution. So if it estimates the intercept, that's part of the full conditional distribution of the coefficients, and it can do that as a group. Whereas it doesn't have a very efficient way to update the cut points, and so it tries to keep as few cut points that it has to deal with as possible. Since Stan doesn't do Gibbs sampling, that's not a consideration. And this just keeps you from having to append a 0 onto that, although that wouldn't be particularly difficult to do if you wanted to do it that way. Then the likelihood, if you look at the .stan file for this, it basically involves a loop over all the observations. We create a linear predictor by plucking out the relevant betas. So year ID is a vector of length n, and it's going to have the integers like 1 to 7 are its unique elements. I think my question was asked in 7 time periods. And so if you extract the ith element of year ID, that's going to be some number between 1, 2, 3, 4, 5, 6, 7. And then that number gets put into the array selection for beta, and it will pull out the betas for that year. So this array of vectors business is almost like a list of vectors in R. Not quite, it only has single bracket indexing, but it basically the same idea. And vectors have to be homogeneous in Stan, whereas in R, the list can have elements of different kinds of things. But in any event, you can create eta for the ith person by multiplying that person's predictors, x, by the relevant betas. Then we need to convert eta into a probability. And this, aside from using the phi approx function instead of the phi function, this follows along with what we talked about before. For the first category, it's just a CDF. For the last category, it's 1 minus the CDF. And for the intermediate categories, it would be the difference of two CDF values. And so this brings us to the issue that people were having, not being able to get the thing to initialize using the phi function. And I think there's nothing actually super wrong with the phi function. It's just the case that if the phi function is input argument less than -37.5, it is going to underflow and return a probability of 0, even though in principle the standard normal distribution goes out to -infinity. It doesn't have the precision to deal with that if the input to it is sufficiently small. And so if your eta minus the gamma business, or gamma minus the eta, for any observation goes below 37.5, phi is going to return a 0. And then when you get to the next piece, I didn't actually put the next piece into the PDF, where you do increment log prob log of p. If any of those p's are 0 as far as the computer is concerned, then it's going to be logarithm of 0, which is going to return -infinity. And then it's going to add some things that involve -infinity. That's just going to be -infinity, and it can't get initialized. And that actually seemed to happen for a lot of people on the initial, to start, because the coefficients it is using are basically arbitrary, and so it could have put some number and multiplied it by age, and age is denominated in years, and so you could get a pretty big shift over. And in any event, all it had to go was like one observation to underflow to 0, and then it's not going to be able to initialize. And so to some extent, that problem could be combated with using more or better initial values, but even that seemed to be not sufficient for some people. And I think most people ended up using the phi approx function, which is very close to phi. It actually uses a transformation and a logistic distribution to approximate the standard normal distribution. It's plenty accurate, but it also happens to be a bit more numerically stable than the real phi function. So the real phi involves a numerical integral, whereas the phi approx, the integral is known in closed form. And so it doesn't seem to have as bad a problem with numerical underflow. I still, in my case, had to change the init R argument from its default value of 2 to 0.01 to get initial values on the unconstrained scale. They were uniform between -0.1 and +0.1. Then I got, a few messages about rejecting initial values and stuff like that, but it tries like 100 different ones before it gave up. And so it was always at least finding some starting value that would allow it to initialize. And after that, it ran pretty well for me. But it's true that I did not anticipate how difficult to overcome that would be for some people and some models. It really depends on what the predictors you were using and the scale of those predictors. If you had some number, that could take big numbers, if it just sort of guessed what the coefficient was, it could easily drive the linear predictor pretty far. And then run into some numerical problems. And like I said last night, if you wanted to change the stand parts to ordered logit, that would be fine. 2, there's a function already in stand to do that, and it's been optimized for numerical stability. So hopefully one way or another, you could get the thing to launch. And then you could, see the results of it. Did you have a question?
Yeah, so this used to happen in real life. Do you just keep like fiddling around and stand until you get it to launch, or do you then like go back and change the predictors that you're using? And
I would say you would only change your model as a last resort. I think that is a general conclusion, or not conclusion, but assertion that I would make, and that should never change what you think is the right model because it's not going with the software. You might be wrong, but if you think that's the right model and the software can't handle it, then that's a limitation of the software. So this is a limitation of the implementation of the standard normal CDF in Stan. So I think the best thing to do would be to fiddle around with the init R. And if that doesn't work, then there's also an option that we haven't talked about of giving it specific starting values. So if you had the maximum likelihood estimates, or you had the posterior means from MCMCO probit or something like that, you could use those as starting values, and that they give like somewhere in the mode. So that would have been another way to overcome the problem. One thing that can be done, which is not really changing the model, but could be an effective idea, is to rescale your parameters, to center them or to standardize them, something like that. So you get, less extreme multiplications. So that doesn't change any of the model probabilities in a generalized linear model. So that doesn't go against my assertion that you should never change your model. Never change your model in a way that affects the likelihood, but you can change the model in other ways, etc. I think if nothing else works, then changing from a probit likelihood to a logit likelihood is not the worst thing in the world if the logit is going to give you more numerical stability. They're very similar shapes. But I wouldn't change the model completely to make it work with any software, inclusive of Stan. And if the model that you really want to run, Stan is unable to do it, and there's no sort of reparameterization or anything like that that's effective, then that's something that we need to address in Stan. And we are working on soon having the ability to specify just some of the initial values. It's kind of tedious to do in Stan because you have to specify an initial value for every parameter. But I think soon we'll have a way to only allow you to specify initial values for some of the parameters, and that might help overcome some problems like these. All right, so that one runs. Then the next one is to think about putting autoregressive priors on the parameters. So those betas are indexed by year, and we're in this situation wanting to express our prior beliefs that the coefficients evolve over time according to a relatively smooth and slow process. There's some computational considerations that I'll get into, but this is a very important substantive consideration. You're changing the model by putting a different prior distribution on the coefficients, but you're doing so in a way that you're unlikely that anybody has a real substantial disagreement with that. There's basically no theoretical models of public opinion where coefficients are just jumping around all over the place from year to year. Nobody thinks that. Now, some people may not totally agree with like autoregressive one, or think about some other form to give some smoothness and continuity to the way the coefficients change over time. but I don't think anyone would object to the general idea. And this kind of goes inconsistent with what I guess most people are sort of reluctant to think about putting informative priors on things, because they think of the process of selecting a prior as thinking, okay, like, what do I think the true value of this parameter is? And then, maybe putting a little bit of variance around that, such that, when the posterior distribution comes back, it won't differ that far from what the prior was. And that sort of gives a sense to a lot of people, particularly frequentists, that, this Bayesian stuff, you're just getting out what you put in terms of your priors. But there's more to expressing prior beliefs than just basically assuming numbers for the parameters and then giving yourself a little wiggle room around that. No one, really does that. Even if they have a number in mind, they're inclined to give, much bigger prior variances than what they really believe. And in situations like these, where we have a hierarchical structure to the data, it's more about expressing your beliefs about how the groups differ or are similar to each other. And we'll get into various ways of thinking about this idea. But in this case, we're not really picking specific parameter values and giving ourselves a little wiggle room. What we want to express is that 2 years are not going to have coefficients that are so different from each other, regardless of what values those coefficients take. We can express that in Stan by using transform parameters for the betas. You can start them in a variety of ways in the first year, but in the subsequent years, it's just phi multiplied by the beta in the previous years. There's another construction here for the intercept of this autoregressive process, equal to the unknown means divided by 1 minus the autoregressive parameters. And again, we're going to use what we call the mat trick to put a standard normal prior on these z's to imply a normal but not standard normal prior conditional for the coefficients. And so that's just another form of the mat trick. And the likelihood is the same as before. You're just referring to elements of beta, and that runs. And the reason why this is more efficient is you can write the joint distribution for the kth coefficient as a marginal distribution in the first year times a conditional distribution in the second year given the first year times a conditional distribution in the third year given the second year, all the way to the last year. But that entails a whole lot of conditional probabilities. And algebraically, conceptually, there's nothing wrong with that. But from Stan's perspective and from a perspective of a lot of software, having posterior dependence in the parameters it's trying to draw from makes things more difficult. So if we reconcile, and if the sigmas for this sort of control how much noise there is in the process, but if sigma is, you get a draw of sigma that's really small, then the range of the conditional distribution of beta has to be very restrictive, and it needs a small step size in order to navigate through that sort of narrow canyon of the posterior distribution. But if you get a draw of sigma that's large, then the conditional distribution of the next beta could be, pretty far away from the previous beta, and it could get away with a larger step size. But unfortunately, what tends to happen in practice in these situations where sigma is not estimated too precisely, it'll use kind of a middle value of the step size, and that middle value of the step size is too big for the region of the parameter space where sigma is small and you get Hamiltonian divergence, and that step size is too small for maybe the bulk of the posterior distribution, and you make very small steps, maybe run into the ceiling on the number of leapfrog steps, etc. both of those can yield poor performance. But if you reparameterize this in terms of z's, put standard normal priors on z's, scale those up to get normal that's mean 0, but with standard deviation sigma, and then shifted over by the autoregressive business, then beta is a transform parameter, and so Stan doesn't have to explicitly worry about the dependence of transform parameters because it's not drawing from them explicitly. It's drawing from the primitives in the parameters block. And the z's in the parameters block are independent of each other. They're independent of sigma. They're independent of all the betas, at least a priori. And so a single step size can be used to navigate around that parameter space. The dependence is not that big, and moreover, it's pretty constant. And so Stan is able to adapt and sample from this model, and it converges, at least in my case, and runs a lot faster than the previous model did. Then the question 7, I intended to be a trick question, but I may have tricked myself. So what I thought was the case, would have been the case, was that adding these shifts wouldn't really do anything of substance because in this ordinal model, there's nothing in the data to separately identify the intercept, all the cut points, and the cut point shift. So this is, you could shift the cut points in a year by a constant. And so like all of them would shift over for the different years, but you have the intercept that's indexed by time also. And so you could shift all the cut points and then shift the intercept a corresponding amount, and it wouldn't change any of the probabilities under the likelihood. And so then you would just be estimating a model where the only information that you have to distinguish delta, which I use from the shifts, and alpha, which I use for the intercept, is your priors, in which case, in terms of the wake, you would just be, estimating more parameters, but not getting any improvement in fit. But the part where I may have been wrong was, with this specific assumption about how the initial period is formed, because we didn't have a beta to lag against. I think possibly there is some amount of information that can be used to identify the shifts, because this model turned out slightly better than the previous one. But I do think if that's true, it's specific to this autoregressive structure thing. In general, if you just kind of had a flat model with an intercept and you had a shift, then it wouldn't be separately identified in the data.
But I think the way you calculate the weight, you don't take the shifts into account, right? So I did a different function because I guess performance you judge that by looking at the wake, right? And so I did a different function for that particular model because you have to take the gammas plus the shifts into account when you calculate the wake, right?
So I did that when I wrote my wake function. We'll get to that. So I think this is a peculiarity with the autoregressive structure and possibly identifying the intercepts. Yeah. Jasper, you had a question?
Yeah, did you have priors on your shifts when you got a better wake? Because the wake I had was like just a little bit worse for the shift modeling.
Yeah, it might have been the case that if you put a sufficiently strong prior on the shifts, then it doesn't really increase the effective number of parameters very much. Mm-hmm. And if, for some reason you get a little bit better fit, it might kind of wash out. Yeah. But in any event, what I hoped people would say was, well, this doesn't make any sense. We're not separately identifying the intercept and the shift, but maybe actually we did. I'll have to look at that a little bit more. So here is my function for the wake thing. It has optional last argument for shift that if that got passed, then it also plucks out the right shift. And so this wake function is very similar to the one that we did in section last week. The only difference is when eta gets constructed, you have to get the betas for that person's year. And so that is going to involve some array indexing. You can see when you pull out the betas from the posterior object, it comes out as 8,000. So I did 8 chains, each with 1,000 things. I had 7 time periods in my model and 15 coefficients for each time period. So I needed to index on the middle thing there. So I passed in the year ID. You have to do that also. And then it'll get the year for the ith person and then select the betas that correspond to that year. The rest of this, I think we talked about last week. So I'll zip through this now. And so what I wanted to happen was that for the question 5, I think for basically any model I can imagine with the GSS, that is much better than the model that doesn't really put any prior structure on the coefficients over time. And in this case, it is, a difference of like 47 on the log scale. And if you're a model that gets beat by 47 points on the log scale, I mean, you suck as a model. And that goes to show that, we got a model, I think, that was a lot better than, what you can easily do in sort of MCMC OPROBIT, or the sort of analogous thing that you might do with maximum likelihood of just interacting year with everything or estimating a separate model for every year. That's actually kind of feasible if you use the whole GSS because it has a couple thousand observations per year. But you would get a model that is not going to predict a new person. We wouldn't expect it to predict a new person nearly as well as in the second model, where we, impose what I would consider to be very non-controversial prior beliefs that the coefficients don't change arbitrarily from one year to the next. And we get a model that seems to fit a little bit better, but moreover has a much smaller effective number of parameters. And so we're not letting our uncertainty in the parameters spill over as much to our uncertainty in predicting a new observation. Now, why it is the third model actually came out a little bit better, still not totally clear, but the third model also had the autoregressive structure. So it was different from I'm not surprised that the third model is better than the first one. I am a little bit surprised that the third model came out better than the second one. But this, is the sort of thing that is not so hard to do in STAN, the second or third model. But it would be like 30 log points better than the typical social science model, but is not so hard to do with STAN, and seems like a pretty reasonable model anyway. So with those weights in the first column, you can calculate the weight or for the probability that this model is going to do best predicting out of sample. That just involves taking the first wake, subtracting the best wake, which in this case would be the third one, and then doing e to the 1/2 multiplied by that. So the third one will come out as e of 0, which is just 1. And then normalize that so you get numbers between 0 and 1 that add up to 1. And you get this for the posterior probabilities for the first, second, or third model, predicting best out of sample. And the first one gets killed. But there's, and 4 out of 5 probability favoring the third model over the second, but not too sure about that. I am sure the first model is probably worse for basically anything that you could do on the general social survey if you're using, a bunch of years. So hopefully people got stuff to run well enough to appreciate that point, which was the point that I really wanted to organize the homework around. Maybe some people didn't get it to run and didn't actually get to see the wake values. But hopefully you can, after seeing the answer key, or hopefully you can at least replicate what I did with the gay marriage question to see that. But I think in general that a model, and Greg Warrow has been, hammering that political science needs to think more about how parameters change over time and to try to incorporate that into the models. And it's not easy to do from a frequentist perspective. It's not hard to do in Stan. So everybody should be using Stan. Okay, so any more questions about that? No?
That's right.
All right. So let's do a little bit about bugs. If you switch over to the zip file for the section today, it just has a couple examples here. So the first thing you need to do is install JAGs, and then there's some R packages that access that that you can install. This is an example that Simon Jackman did related to his class and his book, which was just written a few years ago, but was like a couple of years before we started doing Stan. And his book is like very pro JAGs and bugs, thinking it's sort of appropriate for political and social science research. They should be using that rather than maximum likelihood. I have not specifically talked to him about whether he's using Stan these days, but Simon, if you're listening along with Don, you definitely should. So if we first, so Simon does an example with an ordered logit model, and this is how it would look in bugs, or you should look at it on your screens because you can't see it so well here. Unless I move it over so I can do that. All right. So it looks like this. Bugs models have less structure to them. You can kind of jump directly into the model. So we have a loop over the observations, forming a linear predictor, which Simon should have called Ada. Multiplying different columns of X by the corresponding betas. In JAGs, you can actually do this with some linear algebra, so it doesn't have to be this ugly. Here, we're going to use the logistic distribution. So saying that the logit transformation of Q is equal to the difference of the cut point minus the linear predictor thing. And then we're going to stick those into probabilities on 0 to 1, and then loop over the rest of the cut points, do a similar deal in terms of the difference between the cut point and the linear predictor, and then subtracting those to get the probabilities that feed into the likelihood. Here using the categorical likelihood in bugs to implement this. And so that looks very similar to what we did on the problem set, just using the logistic transformation rather than the normal. He's putting a multivariate normal prior on the coefficients. Remember that because this is trying to do Gibbs sampling, this multivariate normal distribution is parameterized in terms of the precision matrix, not the covariance matrix, precision matrix being the inverse of the covariance matrix, but I think he just makes it the identity matrix anyway. And then he does a normal prior on the primitives for the cut points. So these are not required to be in any particular order. Of course, in the likelihood, we need the cut points to be ordered. So uses the sort function, which is available in JAGs but not WinBugs, in order to get tau, which they are going to be in the right order. So this is basically using transformation of parameters in JAGs rather than Stan. So the model looks like that. We could run it, but we're sort of going out of time, so I'm not going to literally do that. Basically, it's a very similar thing to Stan in that you make a list of data that you want to pass to JAGs, and there's no separate. You don't have to have a separate data block in JAGs. Basically, JAGs just looks at the thing that you wrote down and sees if there's any variable in there that doesn't have a prior. It assumes it's going to get passed in as fixed data. So that's an easy way to make mistakes, but that's how JAGs rolls. Then you can do the thing, JAGs model, which basically does burn-in. JAGs also does some adaptation. So it's technically a warm-up period rather than a burn-in period. And then once it's hopefully converged and all that, then you can call the function coda.samples, passing in the thing that you previously initialized. You can tell it what variables you want to monitor the posterior distribution of, how many iterations, and it will return a coda object that can be analyzed with the coda functionality. And you could run multiple chains and glue them together into a MCMC list. There's also a package called run JAGs, which will enable you to do multiple chains in parallel and return a MCMC list. So hopefully, having already learned Stan, that will be reasonably transparent. The one other thing that I wanted to remind or to give an example of is a problem that we did last year for homework. I guess we're not going to do it this year for homework, but an example where we're trying to model the number of caution flags in a NASCAR race, which is essentially equal to the number of crashes. And the different racetracks in the South, they'll generally have like one or two big races on them per year. And the person who made this data set keeps track of, all kinds of stuff about the races, who won and how many crashes there were. But that might very well be a characteristic that differs from track to track, depending on how fast they are and the number of cars on them and how wide the lanes and stuff are. So we might think there's heterogeneity from track to track. But if we remember from Lancaster, you can't consistently estimate the group-specific parameters as the number of tracks goes to infinity, unless you do one of Lancaster's reparameterizations. And so that's how this would look, I think, with a Poisson model. So here we're saying the likelihood for the ith race is Poisson with parameter lambda. The logarithm of lambda is a linear predictor deal. So this is a function that's available in JAGs. I don't think it's available in WinBugs. In prod to do the inner product or product of one vector with another vector. So in this case, I didn't have to specify it all out in scalar algebra. I just multiplied the ith row by all the elements of beta, and I could specify my x however I wanted. But I also have an intercept that's specific to the track. So I want to pull out for the ith race what its track ID number was, and then get the corresponding intercept from that. But again, can't consistently estimate those unless we use this transformation business where we put a uniform prior on the alpha star. In this case, JAGs doesn't let you put a completely uniform prior over the whole real line because it has to have proper priors, but it's basically the same thing to just do uniform over a huge range. And then do the transformation from alpha star to alpha, which if you remember from the notes, involved dividing by the sum of the linear predictors for all the races that have happened on that particular track. And so this is how I believe it could be done in R. multiplying the lambdas by a column of a matrix that's just zeros or ones that I would have created in R, just using the model matrix function to get a matrix of dummy variables indicating where the race was, and then transform those into alphas, and then we could use the alphas in the likelihood. Again, JAGS doesn't care about the order in which you write stuff down, so you didn't actually see how alpha got created until the end, even though it was used in the likelihood at the beginning, but you just got to get used to that. So in any event, we don't have time to run these. They don't run particularly fast, and moreover, their efficiency is not appreciably better than that our Uneron Gibbs sampler that we created like a month ago or something, maybe more than a month ago. So I can't figure out a reason why you would prefer to use JAGS for a model like this over STAN. But there are situations in which some of your parameters are discrete or some of your unknowns are discrete, in which case it's tedious to impossible to do those currently with STAN. And perhaps the best alternative in general is still JAGS today. One of those situations that will come up is when you have missingness on discrete unknowns. And we will get into that along with missingness generally starting next week. And I will put up a couple readings for that on the syllabus this afternoon. Okay, so any questions about that?
If bugs and JAGs aren't sort of executing code sequentially, I don't understand how it's actually doing that.
Yeah, that's a great mystery. Basically, it reads the code but doesn't execute it, makes the directed acyclic graph that corresponds to this model, figures out from the directed acyclic graph what is conditionally independent of what, and then tries to come up with some optimal visiting scheme as to which distributions it's going to sample from. And then it goes off that. And so in JAGS, you actually have to write the code in order to imply the DAG. In WinBugs, you can just draw the DAG directly and not have to write the code. So this is basically just text. It's not actually code. So it basically, the JAGS reads this like a novel and then figures out the right way to do it.
So I thought the DAG thing was sort of like a tool that certain people could use if they needed to, but it seems like by necessity, it creates a DAG.
Yeah, it doesn't actually show you the DAG in JAGS. It just has like an internal representation of it. But the idea of bugs is basically to get into picture form, and then you can infer what's conditionally independent of what, so you can figure out what are the full conditional distributions of these things, and then do pattern recognition stuff to see if any of these full recognitions are in its database of distributions, and draw from that rather than having to do some fallback approximation black box thing. So it's actually pretty clever.
If it sees a U, it thinks, okay, I've got a beta distribution.
If it sees the kernel of a beta distribution. So it is actually very clever, particularly at its time. It doesn't necessarily translate into efficient sampling, but it did enable people to proliferate bugs models, at least write them down in a general way, and to have it run without necessarily crashing. In any event. Okay, that's all for today. I'll see you next week.